Okay, so I'm going to start going over this little practice final exam. So here are the first two problems. We want to use some kind of substitution to find these integrals. So we'll look at this first one. What I'm going to do, I think, is let u equal the entirety of this radical, the fourth root of x plus 2. If I do this method, what I need to do is raise both sides to the fourth power and then solve for x. Now, the idea here is I've got an x here I need to do something about. So I'm going to let u be that entire radical. And now I know that I can substitute in for the x, u to the fourth minus 2. Now let me find uh, something for the dx. So I'm going to implicitly differentiate. So I've got 4 u to the third du equals dx. Now I can put everything in. So here we go. I've got, in place of x, I've got u to the fourth minus 2. And then I've got, in place of that fourth root, I've got u. And then 4 u cubed du. And there we have it. So now this is an integral that we can deal with. But notice what I have. Let's carefully notice what I have here. In place of the x, I've got what x equals right there. In place of the u, well, I just let u be this entire radical. And that's, or in place of the fourth root of x plus 2, that's the u. And then the 4u cubed du, I put that in place of the dx there. So we've got everything covered with this, and nothing's left to do but go ahead and, well, we can simplify a little bit. We've got 4, and then we've got u to the eighth minus 2u to the fourth du. Believe if I didn't leave something out. So I distributed u to the fourth through. And then we're set up to find our antiderivative. 1/9 u to the ninth minus 2/3 u to the fifth, or what am I doing? 2/5 u to the fifth plus c. There we go. 1/9 u to the ninth minus 2/5 u to the fifth. Yeah, that's it. That's it. Okay, now this other one. We also use substitution on this one. But what I'm recommending, the way we approach this is let's go ahead and split up this top. Let's call it x squared times 2x dx. See, instead of 2x cubed, let's just call it x squared 2x dx. And then down here, we've got the x squared plus 3. So watch what I'll do. I'll let u equal x squared plus 3. That means that u minus 3 is equal to x squared. So I can put that in right here for x squared. Now, we got du equals 2x dx. Ah, look at that, 2x dx. Well, there is 2x dx right there. So let's see what we have now. If we put everything in, in terms of u, here's what we've got. We've got, in place of x squared, I've got u minus 3. In place of 2x dx, I've got du. And in place of x squared plus 3, I've just got u. There. So that looks like we've got everything covered there, right? So we've got, in place of x squared plus 3, there's that, there's that. We put a u in there, and in place of x squared, we've got this. Okay, it's in place of x squared, and then in place of in place of um, in place of 2x dx, we've got du right there. Okay. Now it's just a matter of, you know, dealing or doing a little bit of more work with this integral. We've got u over u, that's 1 minus 3 over u. See? I just took the u minus 3, gave u, made it a numerator over u, and then minus 3, it's a numerator over u. And now here's what we've got. We've got u minus 3 log u plus c. And there we have it. So it worked out nicely when we made those substitutions. Now we want to explore a couple of integrals and use the integration by parts. Okay, so remember, integration by parts goes like this. It says if we've got an integral, let's do this. The integral of u dv is equal to uv minus the integral of v du. Remember, that's the what we call integration by parts formula there. Now, let's see how we could apply that here. I'm going to let u equal x. And the reason I do that is because I would like to end up with an integral that didn't have a product of two functions. In other words, I've got x e to the 2x here. I would like to end up with an integral over here, this v du, where I just had like e to the 2x dx, something like that. In other words, I want to get rid of that x. Now, by letting u be x, when I differentiate it, it drops a power. And for x, the poor thing only has one power. So when I differentiate x, it just goes to 1. Then I let dv be the rest of this thing. And then I get an antiderivative of it. Yeah, 1/2 e to the 2x. You have to be careful because the tendency is to go ahead and multiply by 2 instead of divide by 2. So you have to really watch your bad self on those type problems. But now let's see what we've got. So we've got x e to the 2x is equal to uv minus v du. Ah, look at that. It's nice. This is what we wanted. We wanted something we wanted something that didn't have that x. So now let's see what our antiderivative looks like. It's 1/2 x e to the 2x minus 1/4 e to the 2x plus c. Now that one's complete. Now this one over here, we go through the same process with this one. However, with this one, you've got x to the third power. So if we let u be x cubed, which is what we would do here, what's going to happen is the derivative is going to be 3x squared. So we're still going to end up with an integral with x squared in it times a trig function. So we want to avoid that. What we would end up having to do is we'd have to do integration by parts multiple times. But there's a shortcut. Remember, there's tabular integration. And what we do with tabular is we start off with x cubed and we start differentiating it. 3x squared, 6x, 6, and 0. See, I just start differentiating that x cubed until it's nothing. Differentiate it once, 3x squared. The next time, 6x, 6, and then 0. Then we take this other thing, sine, and we anti-differentiate. So the antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is cosine. And the antiderivative of cosine is sine. We keep doing it until we're lined up with the 0 down here. And then I just make little lines, little diagonals, and alternate plus, minus, plus, minus. And at this point, we're ready to write out the answer. It's just going to be a product of these things. So what we're going to have is we're going to have negative x cubed cosine x. See? Because of the negative right there. The next one's going to be positive. See? We have this negative and this negative. That makes a positive. So we have 3x squared sine x. Okay, that one's. And then we have plus 6x cosine x. And then finally minus 6 sine x and then plus c. And there we have it. Okay, now let's look at some trigonometric integrals. We'll start off with these ones. Now, whenever you see just sine or cosine raised to an even power, if you see even powers of sine and cosine, and there's no odd powers in there anywhere, you automatically think of this identity. Sine squared theta is equal to 1/2 minus 1/2 cosine 2 theta. Now that's in the case of sine. In the case of cosine, you get 1/2 plus 1/2 cosine 2 theta. Okay, this is what you keep in mind. You keep these formulas in mind, power reducing formulas. Okay. Now, I need because it's easier for us to integrate cosine 2 theta than sine squared. So here's what I want to do now. I'm going to use that formula. I'm going to write 1/2 1 minus cosine. Now be careful, it's 6x. See, it's double what's in there. When we had theta in there, it was 2 theta. But we don't have theta in there, we have 3x. So double that, 6x. Well, now this is an easy problem for us. We have 1/2 times x minus 1/6 sine 6x. Yeah, that's all there is to it. There we have it. Now, if you want to check it, you're maybe not sure, you can go back through and differentiate it, and you'll get what you're looking for. Now, this next one over here, we've got cosine cubed, so we've got an odd power. Now, here's what you think about when you see odd powers of these trig functions. You think about sine squared theta plus cosine squared theta equals 1. Now, let's see how we could use that. I'm going to rewrite this function, cosine cubed, as cosine squared x times cosine x. Now, the reason I did that is because I can use this Pythagorean identity right here to rewrite cosine squared as 1 minus sine squared. Now notice, if I just let u equal sine x, then du is cosine x dx. Perfect. That's what that is. So now my integral becomes 1 minus u squared du. Yeah, very simple problem now. So this is going to be u minus 1/3 u cubed plus c. There we have it. Okay, let's look at a couple more. Let's look at a couple involving tangent and secant. Now, first of all, this one is very straightforward because if I just let u equal tan, then du is secant squared x dx. So that makes this one really easy. It's just u du, which is 1/2 u squared plus c. Yeah, so that one's pretty easy. Now, let's look at this other one. Here we have secant raised to an odd power, uh, tangent raised to an odd power. The thing is, we have secant and tangent together. Whenever we see those together in an integral, we're thinking about this formula. Tangent squared theta plus 1 equals secant squared theta. We're thinking of this Pythagorean identity. That's going to help us out. So here I've got that identity that I keep in mind. Now, that's only part of it. We also remember this, that the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Now, what we want to be able to do, well, let me show you. I think just proceeding, uh, you'll see. What if I do this? What if I peel off a tangent and peel off a secant so that I have secant x tan x dx? Now look what I've done. This right here is the derivative of secant. So if I let u be secant, there's the du part of it right there. But I've got a problem here, and then I've got tangent squared. That's not a real problem because of this Pythagorean identity. In place of tangent squared, I can write that as secant squared x minus 1. Yeah, see? I just subtract 1 in the identity and you've got it. Times secant to the fourth x, and then secant x tan x. Yeah. Now I can let u be secant. Okay. So if I let u be secant, then du is secant x tan x dx. Ah, there it is. That's what we wanted. So now we have u squared minus 1, u to the fourth du. And we have tamed that integral down. See? Looks much easier. And of course, we have now a u to the sixth minus u to the fourth. Yeah, there it is. 1/7. So it looks like it's going to be 1/7 u to the seventh minus 1/5 u to the fifth plus our constant. Yeah, that's it. That's it right there. Okay, now we'll look at a couple of trig sub problems. So what you need to keep in mind with trigonometric substitutions is this little box here, this blue box in the middle. This is kind of a guide to how you're going to make substitutions. We choose these ones because notice the derivative of sine is positive, the derivative of tangent is positive, the derivative of secant is positive. If we chose to, for example, let x, in this case up here, be a cosine, well, then we're going to end up with a negative derivative. This is an easy uh, guide to substitution, to use sine, tangent, or secant, because all their derivatives are just going to be positive. Now, we're just using these trig functions and their properties. So we're going to assume that we can take the square root of like cosine squared x. We're going to assume that that's just cosine. We're going to assume that it's positive. In other words, we're going to assume cosine is positive because we don't really care. We just want to use the properties of these trig functions. And after we use those properties, we're going to put them away and then get to the antiderivative. We're just trying to find the antiderivative for this thing. So let's look at what we're talking about here. This is 16 minus x squared. So I just let x be 4 sine theta. Therefore, dx is going to be 4 cosine theta d theta. So I rewrite my integral this way. In place of dx, I write 4 cosine theta d theta. Down in the bottom, I've got 16 sine squared theta. See, all I did was I put 4 sine theta in place of x. And then in here, I've got 16 minus 16 sine squared theta. See? Now, one of the things, here's what we're going to do. We're going to, I'm just going to factor a 16 out of this radical. So here's what's going to happen. And let me just divide out this 4. So I've got cosine theta over 4 sine squared theta. And then I've got 4, 1 minus sine squared. See, I just factored the 16 out of here. So what happened is I've got this 16, which I factored out, took the square root, and I got a 4. Okay. So now let's see what we've got here. We've got 1/16 out front, and I've got cosine theta d theta. I guess I forgot the d theta over here. Sorry about that. And then I've got sine squared theta. And in place of this 1 minus sine squared theta in the radical, let me just put cosine squared theta. Now, here's the thing. I'm just using this property. I don't, I'm assuming I can do this. I'm going to take the square root of cosine squared theta and just call that cosine. Now, normally you wouldn't do that. Normally you take, for example, the square root of x squared would be the absolute value of x. But like I say, we're just using the properties. We're not really concerned about that. So I've got cosine over cosine here. Let me just divide those out. And then let's see what we've got. We've got 1/16 d theta over sine squared, which is 1/16 cosecant squared. Now that is negative 1/16 cotangent. Yeah, there it goes. Now, we're done with the trig functions. We can now go back. We've used the properties of these trig functions. Now we want to go back and put things in terms of x, like we found them. Now remember, we started off saying x is equal to 4 sine theta. That means that x over 4 is equal to sine theta. Let me draw a triangle here. Okay, so I've got theta, I've got x over 4, and that would make this down here 16 minus x squared, just using Pythagorean theorem. So you can easily find out what cotangent is. We've got negative 1/16. Cotangent is adjacent over opposite. Yeah, plus c. There's my antiderivative. And that one is done. Now let's look at this other one. Okay. This one is 9 plus x squared. So let's let x equal 3 tangent theta. Then dx is 3 secant squared theta d theta. Now let's see what we've got here. If I put this all back in the integral, up top I've got 3 secant squared theta d theta. And on the bottom, I've got 3 tangent theta. And then 9 plus 9 tangent squared theta there. Now, one one place people make mistakes a lot of times is they'll forget to put in this dx. They'll forget to substitute in the dx with this thing right here. In other words, they might just change instead of dx, they might just call it d theta. So be careful about that. Okay, now let's see what we can do immediately. Those 3's cancel. That was quick. Now let's see what we've got here. We've got secant squared theta over tan theta. Let me factor out those 9's and get 3 times 1 plus tangent squared theta d theta. Okay, so I just look here, make sure I'm not making any mistakes. Now this 1 plus tangent squared theta is going to be secant squared theta. So let's see what we've got here. I've got 1/3, just bringing that 3 out. secant squared theta d theta over tan theta, and then this is the square root of secant squared theta. And let's see what we can do now. We've got 1/3 secant squared theta over tan theta secant theta, and then the d theta. Mustn't forget that. And then this one gets rid of one of those. And let's see what we've got then. We've got 1/3 secant theta over tan theta d theta. Now let's see here. This would give me 1/3. You've got 1 over cosine up top, sine over cosine on the bottom. So that's just 1 over sine. You can check that out if you want. But I'm just dividing 1 over cosine by sine over cosine. You flip it and the cosines cancel. So now it looks like we have this. We have 1/3 cosecant. Well, now I need to figure out what is the antiderivative of cosecant. That's what I need to do. Now, you can look this up, but I'm going to go ahead and investigate it my own self. So here I go. I've got cosecant theta. Now, I'm going to do this little trick. I'm going to multiply the top and the bottom by cosecant theta plus cotangent theta. I'll do that to the top, and I don't need a parentheses down there. Cosecant theta plus cotangent theta d theta. Let me see. Okay. I just did that to the top and the bottom. That doesn't hurt anything. Now, let's see what we get then. We've got cosecant squared theta plus cosecant theta cotangent d theta. And down here, we've just got cosecant theta plus cotangent theta. Okay, now I'm going to let u equal that bottom, cosecant theta plus cotangent theta. If I do that, then notice that du is negative cosecant theta cotangent theta minus cosecant squared theta. Well, that looks an awful lot like what's up top right here. It's a lot like that, except it's, it's positive there. So let me do this. Let me factor out a negative. So here's what I get. I get negative du is equal to cosecant theta cotangent theta plus cosecant squared theta d theta. In other words, I just divided out the negative. That's what I did. So let's see if we can figure out what the antiderivative of cosecant is then. So what we have is we have negative du over u, and that's negative log u, which is negative log, what was it, cosecant theta plus cotangent theta. Yeah, there it goes. Of course, a plus c. So I believe that's it. So we now know what the antiderivative is for cosecant. So I can go back now and finish up this problem. I've got, let's see here, this is going to be negative 1/3 log cosecant theta plus cotangent theta plus c. There we have it. Now, I need to put it back in terms of x's and x's. So I've got remember we said from the beginning here, we said that uh, x was equal to 3 tan theta. So that means tan is equal to x over 3. So here we've got theta. This is opposite over adjacent. And then this up here would be 9 plus x squared. Okay, so let's see what we've got here now. We've got negative 1/3 natural log. Secant is hypotenuse. Well, cosecant is hypotenuse over opposite. Cotangent is adjacent over opposite. Yeah, so that should be it right there. That should be our answer. Okay, so here we go. Put it in yellow. I think that's it. Unless I messed up along the way somehow, but even if I did, that's the process. That's the process you go through. Okay, so now don't get too bogged down on this part that we did here, finding the antiderivative for cosecant. You know, at the end, you're going to have an integral, and you just have to deal with whatever integral you've been blessed with. Here we were blessed with the lovely cosecant theta. So we had to remember what the antiderivative. Now, really, you could look in the book and find the antiderivative of cosecant. It might not be in the same form that I have here, but you can find it. Now let's look at a couple of integrals where we need to use partial fraction decomposition. Now remember, when we're looking at how we decompose these fractions, we've got to remember this, that if we just have linear factors like this first one, it's very simple. You have a over x, a over the first factor plus b over the second. Now remember also that before we start this partial fraction decomposition, you have to have it factored completely. And also remember that the bottom degree of the bottom needs to be bigger than the top. And if it's not, you need to divide. So if the top is bigger, has a bigger power than the bottom, you need to divide and get a quotient. Now, if we have this one where one of the factors is not linear, it's x squared, and it's a over x plus b over x squared. Now, if this were x cubed, you'd have to have plus c over x cubed. You build up to it because you're making allowance for the fact that there could be anything. If you have an x squared in there, you could have had an x in the denominator. Could have an x, you have to make allowance for the fact that one of your terms could have had an x in the denominator to the first power, and then plus c over x. Now notice over here, we've got x squared plus 1. So we have a over x plus bx plus c, okay? We have to make allowance for this combination down here, this x squared plus 1. Okay, now let's see how we would approach this, okay, for this one. So here's what I'm going to do. I've got 5x minus 12 over x times x minus 4. Okay, so here we go. A over x plus b over x minus 4. Okay. Now, once I get to that point, I'm going to add my fractions. So here's what happens. I've got 5x minus 12 over x times x minus 4. I get a times x minus 4, just building up my denominators. See? The a over x, the common denominator was x times x minus 4, so I needed an x minus 4 down there. So I multiply the top and the bottom by x minus 4. I needed an x over here, so I multiply the top and the bottom by x. Now notice these two are equal, and if they're equal, the denominators, you can see the denominators are equal. I only need to worry about the numerator. So I've got 5x minus 12 equals, let me clear all this out, ax minus 4a plus bx. Now I'm going to use a method called equating the coefficients. So here's what I'm going to do. I've got 5x minus 12 equals a plus b. Gather my x's together. Now, if these two sides are equal, then a plus b must equal 5. The coefficients of the x's have to be the same. And negative 4a must equal negative 12. So let's see that this means that a is equal to 3. And if a is equal to 3, then that means that b is equal to 2. So now we can go back and get our antiderivative. So here's what we have. We have now the integral 5x minus 12 over x minus 4. Now I can rewrite that this way. A, which was 3, so I've got 3 over x plus 2 over x minus 4. So here we go, 3 log x plus 2 log x minus 4. And you could play around with the properties of logs if you wanted to, and make the answer look a little different. Okay, now let's look at this next one. See what we can do with this one. I think I'm going to move it down the page a little bit. Okay, so I moved it down the page. Got myself a little more room. So now let's see what we've got here. We've got negative 19 x squared plus 50x minus 25 over x squared 3x minus 5. So let's start our decomposition. A over x plus b over x squared plus c over 3x minus 5. Okay, 3x minus 5. Now we can start the process. And there's different ways to finding A, B, and C. I'm going to just do equating of coefficients. Okay. There's quicker ways to do it, but this equating of coefficients is a good skill to have. So here's what we've got. We've got negative 19x squared plus 50x minus 25. Now let's see what we've got here. We've got ax 3x minus 5 plus b 3x minus 5 plus cx squared. Notice I'm just equating the numerators. So I multiplied each one of these. All I was doing was getting a common denominator, building up each fraction so it would have the common denominator. Now, let's see what we have here. I'm going to clear my parentheses over on the other side. Okay, so here we go. We got 3ax squared minus 5ax plus 3bx minus 5b plus cx squared. Okay, so all I did was clear my parentheses. Now I equate everything together. So here's what I've got. I've got 3a, I'm getting my x squareds together, plus c. That equals negative 19. I take all the coefficients of x squared, put those equal to the negative 19. Then I have the x's, so I've got negative 5a plus 3b, and that has to equal 50. And then all that's left is this negative 5b, and that negative 5b has to equal 25, which means that b is equal to 5, negative 5. Okay, so b is negative 5. Well, if b is negative 5, then that means up here we have negative 5a minus 15 equals 50. See, I just put a negative 5 in place of b. So 3b became negative 15. And this will give us 5a, negative 5a is equal to 35, right? 30, oh, no, not 35. Look at that, 50 plus 15, that's 65. Yeah, like that. Almost made a mistake there. So then a is equal to 65 over negative 5, which is negative 13. Okay, so a is negative 13. Now, I believe we're set to find c, because we just had a, b, and c. So here we go. We've got a is negative 13, so this is going to be negative 39. Just putting a negative 13 in there. Yep. Plus c equals negative 19. Okay. So now we've got c is equal to 39 minus 19. I guess that's going to be 20. Yeah, there it is. So let's see what our integral is now. Our integral is going to be, what do we have? We had a, which is negative 13, over, I can't remember what it was. Oh, x. And then b is negative 5. Let me just do this. Negative 5 over x squared. And then dx, or c, not dx. Let me see. Then we've got 3x minus 5. So this is 20 over 3x minus 5. There we go. Now, we can look back and make sure we got everything. A over x, b over x squared, c over 3x minus 5. I think that's got it. Let me take one more look. Yeah, I believe so. Okay, so this one is going to give us negative 13 log x. Okay, now I'm going to use the power rule for integration on the next one, and I believe what I'm going to get is 5 over x. Yeah, and then plus, now this one is going to be 20 divided by 3 log 3x minus 5. Okay, that was a substitution problem. If you let u be 3x minus 5, you could work from there. Or you could just realize, well, that's linear in the bottom, so it's just going to be the log of whatever that is divided by the derivative of whatever that is. Yeah, there it goes.